Welcome to Lesson 6.1, Angles in Standard Position in Quadrant 1. We're going to work through some of your homework questions from your workbook here, and let's just jump right in. Our first question is, state whether each diagram represents an angle in standard position and explain your thinking. So we know that when we're looking for angles in standard position, we're looking for angles measured counterclockwise from our positive x-axis. So, looking at A, we can see that our angle is measured clockwise from our y-axis. So A is no, not measured from an x-axis. How about B? B, we can see it's measured counterclockwise and from our positive x-axis. So B is yes. It is measured counterclockwise from our positive x-axis. How about C? C is measured counterclockwise, but it's measured from our terminal arm to the x-axis instead of the x-axis to the terminal arm. So C is no, not measured from x-axis. How about D? Well, D isn't measured from any axes, so D is a definite no, not measured from x-axis. Alright, next question. Point P58 is on the terminal arm of an angle theta in standard position. Sketch the angle. So, for standard position, we're here in quadrant 1 with our x and our y-axes and our origin. So we have a point P58, which is going to be 5 from our origin and 8 up from origin. So we're going to have a point P right about there. Let's label it 5, 8. And we'll make our terminal arm from our origin to our terminal point P. Let's label that R. We can see here that we've created a right triangle with side lengths 5 because we went 5 from the origin, and 8 because we went 8 up from the origin. So when we look at our next question here, it says determine the distance from the origin to P. That distance is going to be our R distance that we labeled on our triangle. So we can use our Pythagorean theorem here, which will say R squared equals x squared plus y squared. Looking back at our triangle, we notice that we have an x of 5 and an y of 8. So let's plug those back into our equation here. R squared equals, our x is 5 squared, our y is 8 squared. That becomes 5 squared is 25, 8 squared is 68. The sum of that is 89. Now we have to square root that to get our value for R, which will be root 89. That's our final answer there. Next part. Write the primary trigonometric ratios of theta. When it says that, we're looking for our sine of theta, our cos of theta, and our tan of theta. If you remember from SOHCAHTOA, our sine is our opposite over our hypotenuse. Our cos is our adjacent over our hypotenuse. And our tan is our opposite over our adjacent. Another way of writing that in terms of x, y, and r is our y over our r for opposite, our x over our r for adjacent, and our y over our x for opposite over adjacent. Plugging the values we found in here, we get 8 over root 89, 5 over root 89, and 8 over 5. And those are our, moving on to part D of this question, we have, what is the measure of theta to the nearest degree? So now we actually want to find what our angle theta is. We can do that by manipulating one of our trigonometric ratios. Let's use tan theta equals 8 over 5 because it has a nice fraction there. Having theta on its own, we inverse tan 8 over 5. And plugging that into our calculator in degree mode, that gives us an answer of 57.9946. That goes on, which is approximately an angle of 58 degrees. That is our measurement for angle theta. Alright. Number 5 says, use this diagram to determine the exact primary trigonometric ratios of 60 degrees. So here we're looking for our sine of 60 degrees, cos of 60 degrees, and our tan of 60 degrees. Let's see what we have. From our triangle, we see we have an x value of 1, an r value of 2, but no value for y yet. So let's use Pythagorean to find that. R squared equals x squared plus y squared. Plugging in, we get 2 squared equals 1 squared plus y squared. Solving for y squared, we get 4 minus 1, which is 3. Square rooting, we get a y value of root 3. So now we can take all our variables and plug in for our trigonometric ratios. Sine equals y over r, cos x over r, and tan y over x, which will get root 3 over 2, 1 over 2, and root 3 over 1, which is just root 3. Part B. Use the diagram in Part A to determine the exact primary trigonometric ratios of 30 degrees. So now we're looking for sine of 30 degrees, cos of 30 degrees, and tan of 30 degrees. If we notice in our triangle that we have our angle 60 and we have our right angle, which is 90 degrees. And if we remember from triangle laws that the angles of a triangle sum up to 180 degrees. So if we subtract 60 degrees and 90 degrees, we are left with our other angle equaling 30 degrees. So now looking at our triangle, we'll have a new opposite and an adjacent for that angle. Let's see what we'll get. So for our opposite over our hypotenuse, we get 1 over 2. And our adjacent over our hypotenuse, we now get root 3 over 2. Leaving our opposite over adjacent as 1 over root 3. These are our new trigonometric ratios for angle 30 degrees. Part C asks, how are the values of the primary trigonometric ratios of 30 degrees and 60 degrees related? So, if we look back at both our solutions here, we see that our sine of 60, which equals our cos of 30, and our cos of 60 equals our sine of 30, and our tan of 60 is the reciprocal of our tan of 30. So let's rewrite those down here. Our sine of 60 equals our cos of 30. And our sine of 30 degrees equals our cos of 60 degrees, whereas our tan of 30 degrees equals 1 over our tan of 60 degrees. Hence, we can say the side adjacent to 60 degrees is the side opposite to 30 degrees, and vice versa. Number 6. For each angle below, determine the exact coordinates of a point on the terminal arm of an angle in standard position. So we're only given our angles and nothing else. And we need to find our P of x, y. Well, in this kind of an equation, our hypotenuse, or our R value, is kind of arbitrary. So we could just pick a value for it. Let's say R equals 4. We need to find our x and our y values. Now we know from before we can manipulate our x and y values to equal our r cos r theta and our r sine r theta. So let's plug those in. It will get 4 cos of 30 degrees and 4 sine of 30 degrees. From earlier, we know that our 30 degrees has a triangle with our other angle equaling 60 degrees. So we can use the previous side lengths for this triangle, and they are hypotenuse of 2, root 3, and 1. So from our cut and our sew, that cos 30 is going to be our adjacent over our hypotenuse, which is 4 times our root 3 over 2. And from sew, our sine 30 degrees is going to be our 1 over 2. Our 4 times our 1 over 2, which can be simplified to 2 root 3 and just 2, giving us a point of 2 root 3, 2. For 45 degrees, we do have another triangle that we could use, which is our 90, 45, 45 triangle with sides root 2 hypotenuse and 1 and 1. So let's find our x, which is our 4 for r again, cos 45 degrees, and our y, 4 sine 45 degrees. Using our triangle, we deduce that cos 45 is 1 over root 2, and sine 45 as 1 over root 2 as well, giving us solutions of 4 over root 2 and 4 over root 2, leading to a point of 4 over root 2, 4 over root 2. We can use the same triangle that we used for part A. Now we'll just use our 60 degree angle instead of our 30 degree angle. But we'll have the same side lengths. So, what do we deduce for x and y? Using r for 4 again, cos of 60 degrees and 4 sine of 60 degrees. 4 times 1 over 2 and 4 times root 3 over 2, leaving us with solutions of 2 and 2 root 3 with a point of 2, 2 root 3.